And we need to
Stop the silly jokes.
okay, maybe we try if there will be a problem. I'll try to. Okay, so who are you presenting the speaker? Okay, so good morning, everybody. We are very happy to have a speak and to have the talk by Dmytro Karvatsky, properties of the set of subsums for series of multi-generalized Fibonacci numbers. Please.
First of all, I want to thank you for invitation to the Institute of Mathematics of FAN for opportunity to have a talk in this seminar. I'm very glad to be here in Poland, in friendly to me country. So the title of my talk is property of the set of subsums for series of multi-generalized Fibonacci numbers. Every number x which can be represented as infinity sum epsilon n un, where epsilon n taking values 0 or 1 is called incomplete sum or subsum for series un. The set of all each number, such number we called the set of incomplete sum for this series. Investigation of the set of subsum for convergent positive series has a very deep history. This mathematical object was defined by some mathematician as the achievement set of sequence un. So we can conclude that the set of subsum for series un is the achievement set for sequence un. There exist some investigation such sets for absolutely convergent series or for series with complex terms. In 1914, Japanese mathematician Suichi Kake described this mathematical object, and he proved that the set of subsum for positive convergent series is a perfect set, and it is a finite union of closed intervals if un smaller or equal Rn holds for a sufficiently large n. Number Rn we call the remainder n remainder for series. Or it is homomorphic to the Cantor set if relation un greater than Rn holds for sufficiently large n. This result was generalized by Mignon and Warnish near between 1940 and 1950.
Can you remind me, un is sum up to n, or does n digit, or
Un is just the nth element.
Element of the series?
Yeah, right.
No,
maybe I will.
No, that was the epsilon.
but given the un on sums of partial sums. Un is just the other of the series.
So this is the n term, and this is the Rn.
And what is un? Same as an an. And what is an?
N is some positive.
Just
in general.
equal. Just equal. But
it's a convergent series, right? Is the series an is convergent?
Yes,
Yes.
yes.
Convergent series. Not just series.
okay, but what was about epsilon n? Epsilon n were 0 for 1.
Yes, We just put here some zeros and one and summing up this series. So we have some numbers.
UN is partial sum?
Yes, this is a subsum.
No, but the UN is what.
No, partial.
Is UN the same as AN? Or is UN something
What
different?
is epsilon and what is AN and what is UN?
You moved to A, before you were U.
Okay, that's, I understand.
No,
But
all
how
good.
epsilon, which is zero,
A,
one,
confused spelling.
how epsilon is related to A? That's
It's
not
not
the problem.
epsilon as 0 or 1.
Yes.
You get the object of the UN.
Ah.
Converging C. Now you consider all possible subsums.
all possible.
Sigma, epsilon, and UN.
So
He's right. Because, yeah, but go back and.
какие formulate a hypothesis that the set
You go to the perfect last time because
Go back one slide,
the definition of
to the definition of the UN. Back. Okay, so here we have epsilon n, I understand this, and next, where is UN? Here is UN. UN.
UN is a-
UN is a priori, then you put epsilon as partition.
yes,
Zero
yes.
or one. And UN is given a priori.
UN is some convergent positive term series,
Convergent.
convergent. But some works dedicated to even divergent series. Well, какие formulated the hypothesis that the set of subsums for any convergent positive series is rather homomorphic to the Cantor set or is a finite union of closed interval. In 1980, it was shown that the Cacaeus conjecture is false. So Soviet mathematician Einstein and Shapiro in this work show that it's not true.
Wait, so could you please go to the previous slide? Because you have this, because this is just what it says. So if we have a, if this first situation holds, then we have a what? We have a finite union, and if the second holds, we have a Cantor set. So this counterexample is somewhere in between. Am I right? So this counterexample is the third situation.
Yes,
Neither the first one nor the second. Okay. Okay.
I understand your question. We can define Cantor set as the set of subsum for series for next series.
Okay.
So in this case, this is the third variant.
But can you, can you return to the previous slide?
It's
No,
impossible.
they want the next one. Oh, so, okay, so I still don't understand because it seems that he formulated the conjecture, which was verified by the previous slide.
No, it isn't. Because
What's the difference?
no, because in the previous slide, could you go to the previous one? Sorry, one last time to the previous one. Because in the previous one, you have this assumption on the remainder of the series. And if the first one happens infinitely often, and the second one happens infinitely often, then
Only
none of
those, but I believe this would be true
Yeah.
always.
Yeah,
and that's
yeah.
not-
So какие things that the set of subsums can be only or finite union or homomorphic to the Cantor set. And he thinks that there is no some another topological type of this set. In 1988, American mathematician showed this example, this in some sense simple series which contain which set of subsum for this series contain interval 3, 4, 1. But it is not a finite union of closed interval. This set X, we defined it as X, has property of some nowhere dense set and infinity union of closed interval. Is some mix of these sets, and this is very interesting set. As a result of Newman, Science, and Guthrie papers, they make next statement. If E is a set of subsum for any positive term convergent series, then E is one of the following topological type. If a finite union of closed interval, some set which homomorphic to the Cantor set, or third variant, it's M Cantorval or symmetric Cantorval. Or they write that this set is homomorphic to the set X of subsum for this Guthrie-Nymann series. For this series. Interest in study of Cantorvals is quite high now. A large number of articles are devoted to such research. In particular, for Cantorval X generated by Guthrie-Nymann series, solved some metric, topological, and probabilistic problems. You can see imagine of this Cantorval. So as you see, the Cantorval contains some closed intervals, like 2/3 to 1, for example.
Can it be both points and intervals? Or just only intervals, or just control? Is mixture possible?
It's some mix. In general case, we don't know.
So we say maybe the points and also intervals.
It's some union of, let's in
When you build
in simple words, it's some union of some nowhere dense set and infinity union of closed intervals. In simple words.
It's possible.
Yes. Also, Polish mathematician Lebesgue, Walczynska in their work on the center of distance calculate the Lebesgue measure for this Cantorval X, and they made it only on 2018. They calculate Lebesgue measure for this simple case, the simplest Cantorval. The Lebesgue measure was also calculated for some other Cantorval, different modification of X in work of Michal Banakiewicz, the Lebesgue measure of some M Cantorval. Another
set is in the real line. The Lebesgue measure is 1, but the set is bounded.
Yes, it's bounded because the series is convergent.
But it is bigger than
One moment.
no, it is contained in.
No,
No, it is from 0 to 5.
you see, 5/3. This set is bounded for convergent set. Because the sum of the series is equal to But for divergent series, it can be a real line. For example, if you consider for harmonic series, you will have semi-line. Yes, am I right? But in case convergent positive series, it bounded by R, by sum of this series. Another interesting problem in this case is to investigate the set of uniqueness for this Cantorval. What is the set of uniqueness? This is the set of all number which have only one sequence epsilon n. Such x can be represented as sum epsilon n xn or un. I write here xn. So you know some number from the set of subsum can have many such sequence epsilon n.
Are these people in the woods? Well, I think Shimon won by.
Shimon Marchinsky, Polish mathematician.
No, but here you have one. This is from Shimon, I think. I think he's in the woods, I'm not sure. No, you didn't meet him.
No.
But if he is in Poland, you can meet him.
He work in lots.
Yeah, that's what
I see, yeah, that's I see, but I didn't met him before. And they prove that the set of uniqueness for this Cantorval X generated by Guthrie-Nymann series is dense in Cantorval X. In this case, this is very interesting result. Another paper is the paper written by a Ukrainian mathematician devoted to investigation of Cantorval, which is a set of subsum for series having the next properties, where the sum of series is 1 equal to 1 and the next limit is equal to plus infinity. Moreover, for any epsilon greater than 0, there exists one series from this family which has Lebesgue measure greater than 1 minus epsilon. So they describe some family of such set. Interesting family. Another papers devoted to investigation of set of subsum for such series K1 plus K2 and so on, as you see, where K1, K2, Km some fixed integer, Q belong between 0 and half. Of this series are elements of multigeometric sequence. This result was generated by American mathematician John Ferdinand and Timothy Ferdinand, a family of Cantorval. So mathematician, there is no sufficient and necessary conditions that the set of subsums is a Cantorval or homomorphic to the Cantor set. Despite essential progress for some series, the problem is quite difficult in general case. In this context, scientists focus on series such that their term are elements of some sequence with some condition of homogeneity, depend on finite numbers of parameters and defined by a formula for general term or some recurrence relation. Many years ago, I studied Fibonacci generalized sequence and use it for representation of real numbers and describe some objects, some sets with difficult local structure. Next definition we have. The sequence of real number un having the properties un plus 2 equal p un plus 1 plus s un, where u1, u2, p, and s fixed real number is called a generalized Fibonacci sequence. So it depends on 4 start parameters. For classic Fibonacci sequence, these parameters are equal to 0. Oh, to 1, yes, to 1, sorry, to 1. The general term of this sequence is determined by formula. So we have next for Binet type formula for this sequence. Next, this is my main object. Let us consider series K1 U1 plus and so on Km U1 plus K1 U2 so on plus Km U2 plus and so on K1 UN plus so on Km UN, where UN is some generalized Fibonacci sequence. K1 is greater than K2 and so on Km are some fixed positive integer numbers. We will call this series as the series of multi-generalized Fibonacci numbers.
Can you progress the slide with this exponential formula?
So what I'm doing is in relation to the previous slides. Instead of taking a geometric series, you are taking Fibonacci sequence.
Yes.
Fibonacci is also exponential minus exponential.
Yes, it's more or less
like
yes,
like pi minus psi.
yes, yeah, well,
That's how I made it.
Yes, you are right. So
maybe I'm right.
So for multi-generalized sequence, for multi-generalized series, we have that un is equal to q on to the n power, and here we have, you can just write that it's some q1 on n with some alpha and beta. Alpha and beta is u2 minus u1 psi over p minus psi. In some cases, for example, for K1 equal to 3 and K2 equal to 2, and next sequence UN equals to 1/4 to the n power plus 1/60 to the n power, this series has form. As you can see, this series is some perturbation, some modify of Guthrie-Nymann series. And the set of its subsum potentially can be a Cantorval. But we don't know, in general case, we don't know, but the terms of this series satisfy following inequalities. So as you can see, the sum of this series is equal to 2, and R to M is smaller than A to M, R to M minus 1 is bigger than A to M minus 1 for any M in M. Next theorem. The set of subsum for this series is a Cantorval. We define it as X plus, which has Lebesgue measure equal to 14 over 13. We can imagine this Cantorval as following in following picture. Maybe I will say a few words about calculations with Lebesgue measure. So for this case, it's simple case. How we can calculate this Lebesgue measure for this X? I show that if we take out or cut of this, for example, central interval from this X plus, we will have two affine copies of all this Cantorval. When you take out this interval, you will have 6 affine copies of all set X plus. So by using these properties, we can calculate, moreover, these sets is disjoint, не пересекающий, disjoint. So we can, in this case, we can calculate Lebesgue measure for this Cantorval, and it's interesting result.
Disconnected or
What is
not intersecting with what?
between each other? This copy doesn't have. So here we can calculate another, and in general case we can prove that the family of such series has the set of subsum which is some Cantorvals, and its Lebesgue measure can be calculated by this formula. So this is this is some easy perturbation of Guthrie-Nymann series. So let's take next case. When K1 equal 3 and K2 equal to 2, and UN is has next form. So you can see difference. Here we have minus. Previous case was when we have plus. This series has next form, and as I say, the difference is in plus and minus. This term of this series also satisfy following inequalities as for previous series. And we also can prove that the set of subsum is a Cantorval. And for example, it contains interval 34 or 49 over 64.
Wait, so I have one question, because I forgot, I'm sorry. So for this basic Guthrie-Nymann series, I think I remember the names.
Yes, yes.
The Lebesgue measure was 1.
One.
Situation.
1.
So, and then you added kind of a distortion, not a distortion. You added another element.
Tail.
Okay, let's go to tail. You added another element, and then you proved in the previous slide, which is still the previous slide. Sorry. Then you proved that the kind of the Lebesgue measure goes to 1 still. On the next slide, because it's 14 over 13, and here you have a smaller and smaller disturbance, and then the Lebesgue measure is still continuous. It still goes to 1.
Yes.
Okay. And you have the precise formula. Okay, thank you.
if I goes to infinity,
Right.
then our Cantorval this is closer to Guthrie-Nymann Cantorval
Yeah.
because this see this tail is smaller and smaller when I goes to
Yes,
infinity.
you have the same topological structure and the measure behaves as a sheet.
Yes.
It goes on.
And for this case, the set of subsums for this series is also a Cantorval, but we can calculate Lebesgue measure for this case. Why? Because we also can prove that some closed intervals are dense. The set of subsums is dense in some intervals, and from Kakeya result and Guthrie-Nymann result, if the set of subsums is dense in some closed intervals, that it interval contains on it, there is no possibility for the set of subsum to be dense. So we can show here that some interval contained in our Cantorval is contained in this Cantorval. But we can also calculate here Lebesgue measure. Why? Because here we will have two zones Q. How can I say it? These zones is some chaotic intersection of gaps and intervals.
So it's not disjointed. Can it not
Yeah.
be disjointed as in the previous situation? Then you
Yes,
have
yes.
disjoint intervals, and then you now have some disjoint intervals and some small. I assume they are small because I'm guessing on the picture. Some small places with some very crazy intersections.
You say they can overlap?
Yeah.
Yes.
Then the question is what is about
We can also,
measures.
yeah,
That's the problem.
that's a problem. So it's easy to prove that it's a Cantorval in some sense, but we can calculate the Lebesgue measure. We can only find some upper and lower border, yes, for this Lebesgue measure. We can also only find some border for this Lebesgue measure.
No, but I had a different question. Each interval has some Lebesgue measure on this. If they overlap, then you can consider some of characteristic functions of these intervals.
Mhm.
And then you obtain density, which is maybe very big. And the question is whether the probability distribution will be absolutely continuous with respect to Lebesgue. If you have Cantor set measure 0, then of course it is not.
I want to, maybe I,
No, I mean, this, what I told you, some makes sense.
another, I will return to this slide. I will say about one problem for general case for all Cantorval. As they say, Cantorval is some union of some novel-dense set and infinity union of closed interval. In this case, how can I say? All the Lebesgue measure is concentrated on this closed intervals.
Yeah.
In this case, but no dense, as I say, Cantorval is some union of some novel descents and infinity union of closed intervals. But this novel dense set in general case can have positive Lebesgue measure. In this case, all Lebesgue measure concentrated concentrate on these intervals, but in general case, it
Okay, it makes total
it
sense.
cannot be true.
It's kind of the structure of the lower dense spot. Here, I assume the dimension of the lower dense spot is strictly smaller than 1, so that doesn't appear in the Lebesgue measure. And in the second situation, I assume the dimension may be 1. So, but we still don't know what was the measure, if it's 0 or not 0.
Okay.
Okay, well, so I have a very natural question. Could you still go one step back? So, can you do the same? Because in the previous slide with slides with the pluses, you did this. You said that if you take the powers, then you get closer and closer to 1.
Yes.
If you take powers here, do you get closer and closer to 1? Still,
Yes.
I assume you get some estimate, but you still get closer and closer to 1. I'm not sure if I'm asking this question properly. So you have this interval where the Lebesgue measure is. So I'm asking if this interval goes to 1. Do you know this?
I understand your question. Don't know.
You haven't tried it. Have you? Okay, you don't know because you haven't tried, or you don't know because it's much more complicated. I'm just guessing.
So you mean if we take this tail, for example, very small?
Yes. So I'm taking 4, instead of 16 to 1024. That's
I take here 16 because 4 to the 2 power is 16, and it is easy to prove that such set of subsums contains some intervals.
Yes.
There exists some algorithm of approximation this, and we can show density in this set. Another interesting series is the series which is the sum of two multigeometric series with the same numbers k1 and so on kn. So we consider this series, and the term of this series is the sum of terms of two multi-geometric sequence. By from other hand, its term are elements for some multi-generalized Fibonacci sequence such that un equal to next. For this is more general object. And here we have next result. Let k1 is greater than k2 and so on, and km, fixed positive integer numbers. And we define k big as the sum of all k1 from I equal to 1 and to n. Assume that there exists a positive integer n and n0 such each of number n1 and n0 and 0 plus 1 and so on, n0 plus n can be obtained by summing up the numbers k1 and so on kn. Then the set of each is of subsum satisfy following condition. If q2, well, let's think that q2 is bigger or equal than q1 without loss of generality. Yes. And if q2 greater or equal to q1 and greater or equal 1 over n plus 1, then it's a set of subsum for series contain intervals. If q1 smaller than q2 smaller than km over k big plus km, then the set of subsum is not a finite union of closed interval. And if next inequality holds, then the set of subsum is some Cantorval.
So unfortunately, this is still not a full classification, is it? Because if
No.
one Q1 is on the one side and Q2 is on the other side.
Yes, yes. I will talk about this on the end of my talk
Okay.
when I consider open problems. Let's define A big as the all combination of epsilon A K M, where epsilon I taking values 0, 1. So A, this is, we call in Ukraine, this is alphabet for this representation in some sense. If our series satisfy condition next, Q1 smaller or equal Q2 and smaller than 1 over cardinality of A, then the set of subsum is sum over that set or Cantor type set with 0 Lebesgue measure. If our series satisfying condition Q1 greater or equal Q2 greater or equal next fraction delta A over delta A plus K, where delta A defined as follows. By simple words, delta A is the biggest gap between neighboring elements of our alphabet. Then the set of subsum is an interval, closed interval. I will make some remarks.
Wait, so it's exactly one interval.
Yes.
It doesn't contain an interval, it is an interval.
So we will have. We are going to previous slide. If we illustrate depending properties of subsums, of the set of subsum on Q2, we can make next.
I don't think they see you on the internet. Dmytro, they don't see this one.
You try to help
No, actually there would be great.
in this
Yes.
minimal spot.
Or I can change the location as you wish. Where would you like to answer?
Okay, I will do it here. So we will have next.
Yay.
Imagine.
Works.
So here we have number km, k plus. So here we have is not a finite union. Here we have contained interval. So here we have the set of subsum is Cantorval. When Q belongs between these two numbers. But we also have here 1 divided cardinality of A. A Cantor type set. And here we have delta A, K plus delta A. It's
Right, the question. So I have a question regarding the, if I understand the n properly. So small n is the number of consecutive numbers you can get using case. And cardinality of A is the number of different numbers you can get using case.
Yes,
Oh, thank you.
yes.
So I think I understood good.
But we still don't know which property has the set of subsums for this in this case and in this case. Here rather it will be a finite union of closed interval, but here it's difficult question. Another question is about Lebesgue measure of this set. We don't know, and demand if it's zero, maybe we can calculate Hausdorff-Bezikovich dimension for this set. It's open problem.
Wait, can it happen that the left gap does not exist? So it can happen that the cardinality of A is exactly n plus 1?
No.
Because K is bigger than 1 or something. K1 was bigger than 1, was bigger than 1? Or?
This number is always smaller than this. But in some case, these two numbers we can have next for some km we can have next imagine. So here we will have k plus km. So this number will be bigger for some km. We think that km is fixed. What would I say? Technique, this technique, which I used to prove this, doesn't work for Guthrie-Nymann perturbation. So there is no some general technique, some general methodic to prove the Cantorval. Every case needs some special key in some sense. How many times do I have?
30 minutes.
40 minutes, okay. So I want, can we close this presentation? And I will maybe, I want to talk about some another interesting series and want to.
Maybe I have this question before we switch to the problem. So you have this three types of Cantor set Cantorval for any union of intervals.
Yes, yes, sure.
Is it somehow true? Maybe I have from intuition that if you consider some convergent series which has this property, you know about it, it belongs to one of three types, you know about it. If you perturb it by adding like some very fast convergent series to it, so that would it preserve as a type, or it's not preserved? In a way, in this three set, this convergent series, it's fine one of these three types, form like open set in that sense.
If we have a fast convergent series,
Well, if you add fast. So we have yeah. So in a way, we have our interval one of three types, and we add to it a series which converges very fast. So whatever you want. Then would it change? Might it change the type? For example, initially there was a Cantorval, the set of subsums.
But for each example, you need really fast
Maybe I
No, not some general. Or,
yeah. Yeah, but
It's
still,
question of stability.
yeah.
We don't know.
So it's not clear. Yeah.
It's not clear.
So it's basically the question of those question marks, because if you are at the end of one of those lines, you are in a kind of this sticky situation. And so, for example, if you are in the barbed wire sector, you can go to the left, and you are at the very end, and then what happens to the left? Because that is definitely a small perturbation.
Okay, can I write here?
Yes, so now I moved it there.
Okay. I want to consider next convergent positive term series.
If X is close to 0.
Where x belong between 0 and 1.
Then we check.
And as for previous case,
Okay, between 0. No.
as in previous case, let's define k big as the sum of all these kn. Okay, I will formulate next theorem, next statement. Theorem 1. If series an satisfy condition then its subsum is not a finite union why I supposed to consider why I consider this series? We know that function sinus x is close to x near 0 point. So this series is potentially has the set of subsum which is a Cantorval in some sense, but this series is something new.
It's not geometric, but it's close to being geometric.
I call it multi-geometric series, maybe, because for we multi-trigonometric series, I think. Okay, let's prove this statement. To prove this statement, I show that AM is bigger than RM for infinity numbers of n. So for any I in n, we will have that AMEI equal to AN sinus X Y. And
Excuse me, could you move the camera?
Yes.
Thank you. Thank you. Oh, it's a little bit blurred.
Let's wait a second. Does it go?
No, it's blurred.
Okay. It is better?
Oh, yeah, it is good, good, good. Good for a moment, but now yet again.
The problem is I don't have a laptop. I don't see it. I can sit there and check, but maybe on the other side it was better.
No. I wrote two chats that it's not visible.
I see.
do you have any question about this? So we just, we just check these inequalities. We check these inequalities on this plane. So, or in this plane.
So just the AMs,
Yes.
the last part.
Taking into account
It's good.
Yeah.
Thank you. Good.
Pascal's inequality. Which have formed taking into account Jordan's inequalities, which has formed next, we have next. So RMI would equal to chi. So is smaller than n. What is equal to k x for AMI, we will have next inequality. It is easy to show. And that for x smaller than 2km AP plus 2km holds next inequality. Any question about this? So we just show that AME bigger than RME for any I for any positive integers E. And from KK result, the set of subsum for this series cannot be a finite union of closed interval. Because this inequality calls for infinity and many n. Okay. Theorem 2. Assume that there exists positive integers and zeros such that maybe we will right here not m but k but such that each of numbers and 0 plus 1 and so on and 0 plus n can be obtained by summing up the numbers K1, K2, and so on, Kn. Or by another word, for any j and 0 plus j.
Okay, so this is similar statement to the one that was before. So this theorem is 2 we are currently writing. This is a similar statement as what in the slide from half an hour.
In some sense, yes, but here we have another condition here.
No, cool. I'm saying this statement
But
about
we just do the same thing for this series.
instead of the
Yes. Because this is my new result.
Yes. I'm just I guess what you're right. I'm not saying it's similar. It's for a non-geometric series.
It's absolutely. Yeah. For any j from 1 to m, there exists such sequence from other words. There exists sequence epsilon m, where epsilon I taking values from 0 to 1, such m plus j is equal to this sum.
J is from 1 to n, but
This number exists in anywhere, in any way. But as I said before, for previous series, this we can have, this picture where the set of subsum can be a Cantorval for some K1 and Kn x. But these numbers exist anywhere. Okay, if our series satisfy condition x be greater or equal to p to n plus p, then a and n contains an interval. Oh. As I say, for any j, we can find such epsilon I, such will whose next quality. From it follows that every number every number t which can be represented as GI sums x to the n power from it follows that every number t which have next form where g I taking values from 1 to m contains on our set of incomplete sum of subsum. Any question about this? So what is this? This is some constant. And what is this? This is some set. Namely, this is the set of subsum for next series. I'm making mistakes that I write here. I define this as m. Maybe we'll define such maybe k. Because we have m here.
Listen, I have a question. So I don't understand this. First, I thought this was okay, so this number j over there, it's not from 1 to m, but from 1 to n, I think. Why is it from 1 to n? Because now this is crucial, and I don't get into how this is m. Why is this as small m and not now it should be capital K if you change the no, not capital K. So what's the j? It's the length of those consecutive intervals, isn't it? So this, if you look at the bottom on the right, you say the numbers start at n0 at n plus 2m.
Yes, and here we will. I make a mistake that I
K, so now j shouldn't be to k.
we change. Okay, yes, okay. Okay, that's my fault.
And it actually can be from 0 to k. Okay. Because you also get that 0. So, okay, so from 0 to k, and now I take it different series, don't take this. Okay, change the series, okay, now I get it. You take K, so you don't take M, like in the previous situation, you take K. Take something completely different.
So this is the constant. This set is equivalent to the set of subsum for this area.
Yeah, that's different.
And we just show for maybe will not end of all this proof, but we show that for
Why each block will take the K times, maybe something in between 0 and.
Yes, but we take subsum.
no.
We take subsum of this whole series.
Here you take J times the same sign Xi, and here you take.
Ji taking values from
Yeah,
0 to
and
K.
here at the bottom you take precisely K times, why not J?
To jest cały szereg.
This is the whole series, and you just choose subseries.
Subsums. So what you said, so this on the top is the set of subsums on series at the bottom.
Yes.
Okay.
And we just maybe I will not to end this proof, but I just say that if this inequality holds, that the set of subsum for this series is a finite union of both intervals. Yeah. We just need to show. It is
Plenty of possibilities.
so it is obviously that if we check inequalities in this place that these two terms are equivalent, so we just need to check inequalities R K bigger than A K for this series. And if the next inequalities holds that the set of these subsums for this series is a finite union of closed intervals. And we will have that the set of all such terms is arithmetical sum of some constant and a finite union of closed interval. And the set of all such terms belong to our set of subsums for this series. And we prove that the set of for this the set of subsums for this area contains some interval. And if we have a case when case when if we have this, then set of subsum is because from one hand it contains interval, from other hand it is not a finite union of closed intervals, so it can be only Cantorval. So that's all. That's all. I want to say a few words about problem for this thematic, but some problem I told about some problems. But in general, case, it's quite difficult to prove the Cantorvality of the set of subsum for some series. So we don't have some general technique to do this. We just find some technique for some family of such sized Fibonacci number or multigeometric series. In general case, this investigation is quite difficult. Another question, as I say, is about calculation Lebesgue measure for this set. In some cases, we can calculate this by using some self-similarity properties for some Cantorvals. In general case, we can't do this because there we can have some different bad interception of gaps of intervals, and in some sense it's a problem. It's a big problem. And even for some problems don't or didn't solve for multigeometric sequence. As I say, there is some intervals where
They cannot see this.
okay. For some values of this Q2, Q1, or some values of X, as in this case, we can investigate topological structure of and matrix properties for the set of subsum. We even can find necessary and sufficient condition for this set to be a zero Lebesgue measure. So there's a lot of problems in this research area.
Okay, so
Any question?
so are there any questions offline or online?
Yes, I have a and my question is that you mentioned several results when you could prove the positivity of Lebesgue measure of existence of intervals, but I do not recall any result you mentioned about the host of dimension of the set of subsums. So the host of dimension, are there results in this direction, or not any results?
You mean can we calculate the Hausdorff dimension for this?
Yeah. So sometimes the set of subsums is a Cantor set, and that you never mentioned any results about the host of dimension in that case. So
yes, I plan to do this in future, but I think we can find some maybe border for this Hausdorff dimension, maybe.
You mean bound?
Border up and low.
Up or above.
Yes.
okay.
Because here we can build some cover by using maybe these remainders of series. We will have 2 on n power this remains intervals which has length R calculation of this, but I plan to do this in future.
Thank you.
I think I can formulate better my question 1 hour ago. If you consider all possible epsilons, 0 or 1s,
Yes.
but you can consider them with probability. And then you obtain probability distribution on this.
Infinity Bernoulli convolution.
Yeah,
Yes.
I tell it just having in mind bias was no other question. But not from science, but just piecewise constant. Plus minus lambda and power n or lambda less than 1.
Yes, I consider this object. And then this is the random variables of Jess and Wintner types. Infinity Bernoulli convolution, yes. And I consider this object, and I also had a paper published on random operator and stochastic equation. Dmytro Karvatsky, Lebesgue structure on infinity Bernoulli convolution, but not for this series, for another series, for series of reciprocal Jacob-Stahl Lucas numbers. Yes, some series, but for this, it's very difficult task to investigate this.
But you know.
But the factor of this random variable is will be subsum of the set of subsum for this series. But it equivalent in some case to the set. So we just only say that if this the set of subsum for such period have is the Cantor type set, that this infinity Bernoulli convolution is singularity in any. But if
Not obvious, but maybe there is a chance.
yeah, but if the set of subsum is the Cantorval, it's very difficult. It can be absolutely singularity, absolutely. No, it's very difficult.
Okay, thank you. Okay, thank you very much.
But this is very interesting because nobody do it before.
Yeah.
Maybe we will make some photo for memory.
No, you can summarize, you can make it, it's server, it's no way.
So